welcome. In the last two lectures we reviewed fundamentals of thermodynamics. So now let us review fundamentals of fluid flow in this particular lecture. So the objectives of this lesson are to present equations for conservation of mass, conservation of momentum, and discuss Bernoulli equation and its applications, and discuss methods for evaluating friction pressure drop and minor losses. At the end of this lesson, you should be able to state laws of conservation of mass and momentum, apply these laws to fluid flow problems in refrigeration and air conditioning, and state Bernoulli equation and apply it to simple problems, and finally evaluate friction pressure drops and minor losses using suitable correlations and design data. Now, why do we have to study about fluid flow in refrigeration and air conditioning? As you have probably seen, in a typical refrigerant system or an air conditioning system, we will be handling a large number of fluids, for example refrigerants, air, water, etc. These fluids will be flowing from one point to the other. That means fluid flow is involved in all these systems. Now these fluid flows are subjected to certain fundamental laws of fluid mechanics. So in order to understand or in order to design refrigeration and air conditioning systems, one must know the fundamentals of fluid mechanics or fluid flow. Okay. So that's what is mentioned here. In refrigeration and air conditioning systems, various fluids such as air, water and refrigerants flow through pipes and ducts, and the flow of these fluids is subjected to certain fundamental laws, and the subject of fluid mechanics deals with this subject with these aspects. Probably you have studied the fluid mechanics, so it is not possible to review the entire subject here, but we will be presenting the basics of these things relevant to refrigeration and air conditioning. Now, fluid flow in general can be compressible or incompressible. What do we mean by compressible flow? A compressible flow means the density of the fluid varies along the flow direction. That means basically fluid density varies as the fluid flows. So such flows are known as compressible flows. And in incompressible flow, the density remains constant, it does not vary. In most of the refrigeration and air conditioning applications, the fluid flows can be assumed to be compressible. Why do we assume this? Because this will simplify the problem considerably. So most of the times we assume the flow to be incompressible, and the resulting mathematics will be simpler. However, you cannot just like that apply the assumption of incompressible flow everywhere. You have to see its validity. The assumption that the flow is incompressible is valid as long as the velocity of fluid is much smaller than the local sonic velocity. That means the velocity of the fluid should be smaller than the velocity of sound, or in other words the Mach number should be less than 0.3, and as you know the Mach number is the ratio of velocity of fluid divided by the sonic velocity. So when the Mach number is less than 0.3, you can assume the flow to be incompressible and apply the suitable laws. Now to analyze fluid flow problems, one has to consider three conservative equations. They are equations for conservation of mass, equation for conservation of momentum, and equation for conservation of energy. Conservation of energy is nothing but your first law of thermodynamics, which we have discussed in the review on thermodynamics. So in this present lecture we will be discussing conservation of mass and conservation of momentum. Now depending upon the approach, you can write these equations either in integral form or in differential form. That means if you are taking a control volume and apply these conservative laws, you get integral form of equations. Or if you take a differential element inside the control volume and apply the conservative laws, you get the governing equations in differential form. In the present lesson, I will just give you only the integral forms of conservation of mass and conservation of momentum. Now this equation shows the conservation of mass. As the name implies, conservation of mass in simple terms is that mass can be neither created nor destroyed. Just like energy, you cannot create mass nor you can destroy mass. So if you apply this conservation of mass to a control volume, then you get a equation of this form. As you can see in this equation, you have two terms. The first term here is Okay. So, the first term here I am sorry is the rate at which the mass of the control volume is varying with time, that means time rate of change of mass of the control volume. CV stands here for control volume, and the second term is nothing but the net mass flux out of the control volume. So, the conservation of mass when applied to a control volume gives you two terms, two integral terms, since you are applying integral form. So, this first term accounts for the rate at which the mass of the control volume is varying with time, and the second term accounts for the net mass flux out of the control volume. In this equation, rho is the density, T is the time, and V is the velocity vector with reference to the control volume. Okay, and when the flow is steady, that means when the flow does not vary with time, this term will not be there. So, this equation boils down to conservation of mass for a steady flow situation. So, these equations are also known as continuity equations. So, basically for steady flows we will be having this kind of an equation. Now, if you apply this conservation of mass to a one dimensional steady flow through a duct, let us say that we take an arbitrarily shaped duct, and let us say that this is the control volume, and let the flow be steady and the flow be one dimensional. Since the flow is steady, no mass can be accumulated within the control volume, that means the mass inside the control volume is constant, that means whatever mass is entering, that must leave the control volume. Okay, that is what is written here. The rate at which mass is entering into the control volume is equal to the rate at which mass is leaving the control volume, and the rate at which mass is entering the control volume can be written as a product of density rho 1, cross sectional area A1 at the inlet, and velocity V1 at the inlet. Similarly, at the outlet you can write the mass flow rate out of the control volume as rho 2 into A2 into V2. Oh, so this is the simple one dimensional steady flow equation when you apply it to any duct. Now, if the density is constant, that means when rho 1 is rho 2 is rho, then you get a conservation of mass in a very simple form as A1 V1 is equal to A2 V2. Okay. Right. So, for steady incompressible flow for a one dimensional situation, we get the conservation of mass equation as A1 V1 is equal to A2 V2. Now, when A1 is greater than A2, then the velocity V1 should be less than V2. This is what is known as a nozzle. That means the velocity increases in the direction of flow as the cross sectional area reduces in the direction of flow. This is what is known as nozzle. And when the reverse case, when A1 is less than A2, that means cross sectional area increases in the direction of flow, then obviously according to the conservation of mass equation, the velocity should reduce in the direction of flow, and this is what is known as a diffuser. Now, let us look at the conservation of linear momentum. This is nothing but a mathematical expression for Newton's second law applied to a control volume, and the general equation in integral form is like this. So, here what we have is dP by dt applied over a control volume, this term. This term is nothing but rate of change of linear momentum of the control volume, and this is equal to, according to Newton's second law, is a net force acting on the control volume. This is nothing but the Newton's second law. And when we apply this to a control volume, we can write this and introduce two terms. You have one term here, another term here. This first term accounts for the rate at which the momentum of the control volume is increasing with time. So, this term accounts for the rate of change of momentum of the control volume. And the second term accounts for the net momentum flux out of the control volume. So, in simple terms, the conservation of linear momentum says that the net force acting on a system is equal to sum of the rate at which the momentum of the control volume is increasing plus net momentum flux out of the control volume. This is a vector equation, that means you can write this equation for different directions. For example, you can have linear momentum equation for x direction, linear momentum equation for y direction and z direction. So, this can be written in this form. The net force acting on the control volume can be split into sigma Fs plus sigma FB, where this is the sum total of all the surface forces, and this is the sum total of all body forces acting on the control volume. So finally the linear momentum equation boils down to sigma Fs plus sigma Fb is equal to the momentum rate of momentum change of the control volume plus net momentum flux out of the control volume. Now for steady state, again just like conservation of mass, for steady state you do not have the time terms. So the linear momentum equation for steady state becomes like this, where Fs stands for the surface forces acting on the control surface, and Fb accounts for all the body forces acting on the control volume. So the sum of these two forces is equal to net momentum flux out of the control volume. And what are the typical surface forces? The typical surface forces are pressure forces, forces exerted by the physical boundary on the control surface, etc. Okay, and the most common body force is the gravity force acting on the mass inside the control volume. Now some of the applications of linear momentum equation are force exerted by the fluid flow on nozzles, bends in a pipe, etc. That means we want to find out what is the force exerted due to fluid flow on nozzles and on the walls of the pipe and the bends, etc. Then you have to apply the linear momentum equation, and linear momentum equation is also applied to find the motion of rockets and the calculation of motion of rockets, and it is also applied for in water hammers, etc. Now let me give an example of the application of linear momentum equation. This is a very simple example. What we have here, okay, let me read the problem. We have here a straight rigid 100-meter long pipe through which water flows. Okay, so water flows through this pipe, and it has a diameter of 0.25 meter. Okay, so diameter of the pipe is 0.25 meter. It is rigid, it is horizontal, and it is 100-meter long. And the water enters at certain pressure and it leaves at a pressure that is equal to atmospheric pressure. That means here you have P2 is equal to 1 atmosphere. So basically the pipe discharges water into atmospheric pressure, and at a given instant the flow rate is 0.01 meter cube per second. That means the flow rate of water through the pipe at a given instant is 0.01 meter cube per second, but it increases at a rate of 0.1 meter cube per second square. That means the flow rate through the pipe is not constant, but it increases with time, and the rate at which the flow rate is increasing is equal to 0.1 meter cube per second. And we can assume the water to be incompressible, and we can also neglect frictional effects and take the density of water as 100 kg meter cube. And what we have to find out is what should be the pressure at the inlet, so that water under these conditions can flow through this pipe. So first what we do is we apply the conservation of mass. Even though here the flow is not steady, since we have a rigid pipe, a rigid horizontal pipe, and the water is incompressible, the mass of the control volume cannot change, because the volume of the control volume is constant. So the amount of mass within the control volume is constant at any given instant, so it does not change with time. That means whatever mass enters into the control volume must leave the control volume. Okay, so if you apply this, then you get the conservation of mass equation as A1 V1 is equal to A2 V2. That means and since the area is constant at every place, if it is a uniform cross section pipe, the velocity remains constant throughout the pipe. So this is basically the conservation of mass. Now let us apply conservation of linear momentum. As I have already shown, conservation of linear momentum says that the net force acting on the control volume, so this is the control volume here, I have shown the control volume by dashed line. The net force acting on the control volume consists of the sum total of all surface forces plus sum total of all body forces, and this is equal to the rate at which the momentum of the control volume is increasing plus net momentum flux out of the control volume. That means this term is nothing but at any given instant what is the difference between the momentum out of the control volume minus momentum entering into the control volume. That means momentum at this point minus momentum at this point. Now the mass flow rate is constant at any given instant, and the velocity at this point is same as velocity at this point. So their net momentum flux out of the control volume is 0. That means this term is 0 for this particular problem. And since we are neglecting frictional effects, and if since the pipe is also horizontal, there are no body forces also, so this term is also not there. Then the surface forces in x direction is simply because of the pressure difference at the inlet and the outlet. That means sigma Fsx is nothing but P1A minus P2A, that is equal to A into P1 minus P2, which is equal to pi d square by 4 into P1 minus P2. So this is the net force acting on the control volume in the x direction. So this should be equal to the rate at which the momentum of the control volume is changing. So the rate at which momentum of the control volume is changing is this, and here the small v is the momentum per unit area, okay, which momentum per unit area, and this can also be written as, it is some kind of velocity, and this can be written as volumetric flow rate divided by the cross sectional area. That means v is equal to Q by A. So if you substitute Q by A for V, you get this equation, and if you integrate it over the entire volume, this dV is the differential volume, and the total volume of the pipe is equal to L into A. So this equation becomes d by dt Q by A into rho LA, and A get cancelled. So ultimately you have rho L dQ by dt, and in the problem it is given that dQ by dt is 0.1 meter cube per second, and rho is given as 100 kg per meter cube, and length is 1 meter. So if you substitute this these values here and then use the equations 1 to 4, you get the answer P1 is equal to 304.7 kilopascal absolute. That means the pressure here should be 304.7 kilopascal, so that the flow can take place. This is a very simple application of linear momentum to a pipe flow. And the same linear momentum principle is used in many other applications, and when we discuss the fluid flow aspects through refrigerant pipes and ducts, we will discuss these issues. Now, similar to linear momentum, we can also write a conservative equation for moment of momentum or angular momentum. This equation is known as moment of momentum equation, and this states that the net moment applied to a system is equal to the rate of change of angular momentum of the system. This is known as the conservation of angular momentum, and this is very widely used in hydraulic machines such as pumps, turbines, centrifugal compressors, etc. Now let us look at one of the very important equations called Bernoulli's equation. This equation is applied in a wide variety of fluid flow related problems, and in it can be derived either from the momentum equation or from the first law of thermodynamics. That means either you can use the momentum equation or basically the Euler's equation, or you can also derive the same equation from first law of thermodynamics or conservation of energy equation. And this equation in simple terms relates pressure, velocity and elevation along a streamline, or pressure, velocity and elevation between any 2 points in the flow field. Now I am sure that you have studied about streamlines in fluid mechanics, but let me just give the definition of streamlines. Streamlines are the lines drawn through the flow field in such a manner that the velocity vector of the fluid at each and every point on the streamline is tangent to the streamline at that instant. That means streamlines are lines drawn through the flow field. If you take a point on the streamline and draw a tangent, that gives the direction of the velocity of the fluid at that point. So this is the basic definition of a streamline. Now the concept of streamline is very useful in describing a flow field in terms of speed and direction of flow. If you want to describe a flow field, as you know that it is a vector field, you have to specify both the magnitude and direction. So the concept of streamline is very useful for such a flow field description. And it can be shown from continuity equation that when the streamlines are very close to each other, that means the speed of flow is high. That means, or in other words, speed of flow is inversely proportional to the spacing between streamlines. Now Bernoulli equation is applicable along a streamline under the assumptions of steady flow, one dimensional flow, incompressible flow and inviscid flow. So what do we mean by steady flow? As you know, steady flow means the flow doesn't vary with time. So whenever you have fluid flow situations which do not vary with time, you call that flow as steady flow. And what do we mean by one dimensional flow? One dimensional flow means properties vary only in one dimension. In the other two dimensions they remain constant. That means at any cross section the fluid properties remain constant. If you are talking about one dimensional flow in x direction, that means in y and z direction there are no variations in the fluid properties at any x. So, this is the meaning of one dimensional. And what do we mean by inviscid? Inviscid means the fluid should not have any viscosity. That means this is basically applicable to ideal fluids, because all real fluids have viscosity. So, the moment you say that it is applicable to inviscid flows, that means it is applicable to ideal fluids. And finally, incompressible. Incompressible, as we have seen, means that the density does not vary along the fluid flow direction. So, under these assumptions you can apply Bernoulli's equation to any 2 points on a streamline. And Bernoulli's equation is also applicable to any 2 points of the flow field when the flow is irrotational in addition to one dimensional, inviscid, steady and incompressible. What it means is, if the flow is irrotational in addition to steady, incompressible and inviscid, then you can also apply Bernoulli equation to any 2 points in the flow field, it not necessarily on the same streamline. What do we mean by irrotational flow? Irrotational flow means the fluid particles do not undergo net rotation. So, that is what is known as an irrotational flow. Now, the Bernoulli equation is given by this expression. You can write it in different forms. For example, if you write it in the form of head, that means in the form of pressure head, velocity head, static head and total head, you get this kind of an expression. Here this term, as you can see, is known as pressure head, and this term is known as velocity head, and this term is known as static head. And here P is the static pressure, rho is the density and g is the acceleration due to gravity, and v is the velocity of the fluid, and z is the elevation with reference to a datum. So, basically what the Bernoulli equation written in terms of the head says that the pressure head plus velocity head plus static head between any 2 points in the flow field or between any 2 points on a streamline is constant. That means the total head is constant. You can also write this equation in terms of pressures. That means you can write this in terms of pressures as static pressure P, velocity pressure rho v square by 2 and pressure due to datum. So, Bernoulli equation when written for in terms of pressure states that the static pressure plus velocity pressure plus pressure due to datum, called as total pressure, remains constant under the assumption stated earlier. Now, between any 2 points in the flow field you can write Bernoulli equation in this form. For example, I am writing this between point 1 and 2, then the summation of static head plus velocity head plus head due to datum is equal to the static head plus velocity head plus datum head at point 2. And as I was mentioning, for real fluids the flow is not inviscid, that means viscous effects are there in real fluid. So, you can modify Bernoulli's equation and by including what is known as a head loss term. So, this is known as modified Bernoulli equation. That means it is nothing but Bernoulli equation with provision for viscosity by including head loss term. So, in this expression all these terms are known to you. One additional term is HL, which is called as head loss. So, now let me show the pressure variation. Let us apply the Bernoulli equation to a pipe flow and let us see how the pressures are varying. Let us, what we have here is a uniform cross section pipe through which a fluid is flowing. Okay, and we would like to plot different pressures. Now, let us to start with, let us assume that the flow is inviscid. That means the fluid does not have any viscosity. Since the cross section area is same here, that means area at any point is same. So, if you apply continuity equation, at any point V is constant. So, velocity does not change along the length. Since velocity pressure is equal to rho v square by 2 and rho is constant here, the velocity pressure also will remain constant because V is constant. So, if you are plotting pressure, different pressures versus length, you find that for the velocity pressure you get a horizontal line. Okay, so this is a line for velocity pressure. And if the fluid is ideal, then the static pressure also remains same. So, this is the static pressure line for the ideal fluid. Since the total pressure is summation of velocity pressure plus static pressure, the total pressure line is also horizontal. So, total pressure at any point is equal to velocity pressure plus static pressure, and it remains constant throughout the length. So, this is the application of Bernoulli's law to an ideal fluid. Now, what is the effect if viscosity is non-zero? That means the fluid is viscid or it has finite viscosity. For viscous flow, the velocity pressure still remains same, because from the continuity equation, velocity at any point should remain same. Okay, so this horizontal line applies to both inviscid as well as viscous flows. So, velocity pressure remains horizontal only. Then what happens to the static pressure? Static pressure continuously reduces in the direction of flow because of the viscous effects. That means there is a loss of static head due to viscosity. So, you see the a sloped dashed line for viscous flow. Okay. So, the total pressure is nothing but the summation of static pressure plus velocity pressure. So, and the velocity pressure is remaining constant and static pressure is reducing. So, the total pressure also reduces in a real flow, and this difference between the total pressure at the inlet minus total pressure at the outlet is nothing but your head loss. So, this is the application of Bernoulli's equation to a pipe flow. Now, let us say that we would like to maintain the same pressure at the inlet and as well as the outlet, and the flow is inviscid. That means we want to maintain P1 should be same as P2, and similarly static pressure at the inlet should be same as static pressure at the outlet, but the fluid is viscid, that means it has viscosity. Then how do we ensure this? So, whenever you have viscous flows, and if you want to have same pressures at the inlet or outlet, or if the inlet pressures are greater than the outlet pressures, then what we have to do is we have to use some kind of a pump or a fan. For example, if I am using a pump here or a fan here, okay, then it is possible to maintain the same static pressures and the total pressure at the inlet and outlet. What happens when you have when you are putting a pump? When you are keeping a pump or a fan in the pipe flow, the velocity pressure does not change, because the fan or pump does not increase the mass flow rate. So, velocity pressure remains same, but it increases the static pressure because it adds energy to the fluid. So, at the point where you have added the pump, the static pressure increases. Okay. Since the static pressure increases, the velocity pressure also increases. So, you have the modified pressure lines with the addition of pump or fan inside the fluid circuit. Now, that is what is shown in this slide. This is the modified Bernoulli equation with friction and a fan or pump, and I have shown here an arbitrary cross section. That means cross section area need not be constant, and the fluid enters here and fluid leaves here, and this is the fan or a pump. So, what is the modified Bernoulli equation for this kind of a situation? This is the modified Bernoulli equation, only the difference is this. So, this is nothing but the head gain due to the presence of the fan. If P1 is equal to P1 by rho z is equal to P2 by rho z, and V1 square by 2g is equal to V2 square by 2z, and Z1 is equal to Z2, then these terms get cancelled out, and you have Hp is equal to H loss. That means the head gain due to the fan should be sufficient to overcome the head loss due to friction. Now, what is the power required to drive the fan or pump under the case discussed just now? So, this equation gives what is the power requirement when you are using a fan or a pump. This again is derived by using Bernoulli's equation, and what we have here, this m dot is nothing but the mass flow rate of the fluid, and this is the head loss, and this is the static pressure at the outlet, static pressure at the inlet. V2 square minus V1 square is the difference divided by 2 is the difference in velocity pressures at the outlet and inlet, and this is the difference in the datum heads. And here eta fan is the efficiency of the fan. That means if the fan has some inefficiency, then you have to take that into account. So, this expression gives you the fan power required or pump power required. So, you can by applying Bernoulli's equation, you can find out what should be the motor capacity to drive the fan or pump. Now, let us apply this Bernoulli equation to a very simple case. So, this is an application of Bernoulli equation to a venturi. Now, what is a venturi? Venturi is a device for measuring flow rate. So, basically normally it is used for measuring air flow rate or water flow rate. So, as you can see in the figure, it consists of a straight portion, then a converging portion and a gradually diverging portion. So, this is your diverging portion, this is the converging, and where the diverging and converging portions meet, we call it that portion as the throat of the venturi. And here this is the inlet to the converging portion is 0.1 and the throat portion is 0.2. And the venturi has a manometer here, and one end of the manometer is connected to the inlet to the converging section, that means 0.1, and the other end of the manometer is connected to the throat portion, that means 0.2, and this manometer is filled with some manometric liquid. So, basically the air flows through the manometer, and because of the air flow there will be some pressure difference in the manometer, that means there will be a manometric head here. And from the characteristics of the venturi and from the by measuring the manometric head, you can calculate the air flow by applying Bernoulli's equation. So, now let us look at the problem statement. It is given here that the areas, cross sectional areas A1 and A2 are 0.5 meter square and 0.4 meter square. That means area at this point 1 is 0.5 meter square and area at point 2 is 0.4 meter square, and the density of air is 1.12 kg per meter cube, and manometric fluid used here is water, and it has a density of 1000 kg per meter cube, and the measurements show that the manometric head is 20 mm, and it is also given that acceleration due to gravity is 9.81 meter per second square, and we can neglect all frictional effects. That means we will be applying the original Bernoulli equation, because we are assuming the fluid to be incompressible, steady, irrotational and inviscid. So, frictional effects need not be considered. So, if you apply Bernoulli equation, let us see what happens. First, what is the required output? We have to find out what is the mass flow rate for this venturi, which shows a manometric head of 20 mm. So, the equations for mass flow rate is rho AV, mass flow rate at any point, is equal to rho into cross section area at that point and velocity at that point. So, you can write this expression for mass flow rate, and from continuity equation, nothing but conservation of mass equation, A1 V1 is equal to A2 V2, because we are assuming the fluid to be incompressible. So, rho A at any point is constant. So, from this equation you get that A1 V1 is equal to A2 V2, or velocity at the point 2, that means velocity at the throat can be expressed in terms of the areas, cross section areas at the throat and at the inlet to the converging section, and the velocity at the inlet to the converging section. So, V2 is equal to A1 by A2 into V1. Now, let us apply Bernoulli equation. If you are applying the Bernoulli equation, you can slightly write it in a different form. Datum head is change in datum head is 0. So, we can write the Bernoulli equation in this form: P1 minus P2 is equal to rho A into V2 square minus V1 square by 2, and P1 minus P2 is nothing but the pressure difference between the point 1 and 2, which can be obtained from the manometer reading as rho GH, where rho W here is the density of the water, G is the acceleration due to gravity, and H is the manometric head. So, if you use the input data and these 4 equations, you will find that the mass flow rate of air is equal to 11.18 kg per second. So, this is one very useful application of Bernoulli equation to a venturi meter. There are many other applications of Bernoulli equation. As I mentioned, it is one of the most useful equations, and you find its applications particularly in air conditioning or duct design and in refrigerant piping design, etc. We will be using this equation repeatedly, but you must keep certain things in mind. Even though Bernoulli equation is very useful, you must be aware of the assumptions under which the Bernoulli equation is valid. For example, Bernoulli equation is not valid when you have a duct where there is a sudden expansion. When there is a sudden expansion, what happens is the fluid gets separated. That means there will be separation of fluid, and the flow no longer remains one dimensional. so you cannot apply Bernoulli equation, because you remember that Bernoulli equation is a scalar equation and it is applicable to one dimensional flows. So whenever you have 2 dimensional, 3 dimensional effects, you cannot apply Bernoulli equation, number one. And second thing is, if you have a fluid flow where there is a lot of heat transfer as the fluid flows through the duct, then also you cannot apply Bernoulli equation. Then, because what happens when there is a large amount of heat transfer, then the density may not remain constant as the fluid is flowing through the conduit. That means the assumption of incompressible flow will not be valid. So you cannot again apply the simple Bernoulli equation that we have discussed here. So when you are applying Bernoulli equation, first make sure that the assumptions or the conditions are met, and then apply the Bernoulli equation. Of course, Bernoulli equations are also been developed for unsteady flows and also for compressible flows, but we will not be discussing those issues, and these will be discussed in applied fluid mechanics courses. Right. Now let us look at the evaluation of pressure loss during fluid flow. We have seen that generally in one of the most common problems or common requirements in the design of an air conditioning duct or in the design of a refrigerant piping or in a chilled water piping is to find the capacity of the motor or capacity of the pump. What should be the power consumption, or what is the power consumption of the pump, so that you can select a suitable motor for the pump or the fan. So you have seen from the modified Bernoulli equation in the presence of viscous effects and a fan that the pump power depends upon the mass flow rate, and it depends upon the inlet and outlet pressures, velocities and datum heads, and the friction losses, that means the head loss. So if you want to find out what is the power requirement, you must know what is the head loss. Okay, and normally in any given problem, the mass flow rates is an input, and the pressures and velocities are also inputs. So if you know the head loss, then you can find out the power input. So a key problem here is to find out what is the pressure drop as the fluid flows through a conduit. Now the loss in pressure is due to fluid friction and turbulence, change in fluid flow cross sectional area, and abrupt change in fluid flow direction. That means the fluid undergoes pressure loss due to these three effects: friction and turbulence, change in fluid flow cross sectional area, and abrupt change in fluid flow direction. A pressure loss due to friction and turbulence is known as frictional pressure drop, and pressure drop due to change in cross sectional area and abrupt change in fluid flow direction is known as minor loss. That means frictional losses, all losses due to friction and turbulence are known as frictional pressure drops, and losses due to change in cross sectional area and change in direction are known as minor losses. Sometimes the name minor losses could be a misnomer, because in some situations the minor losses can be much more than the frictional pressure drops. So you have to keep it in mind, and you should not neglect the minor losses thinking that they are minor. Now the frictional pressure drop. The frictional pressure drop is given by Darcy-Weisbach equation for internal flows, and it is given as delta Pf is equal to F L by D into rho V square by 2. This is the frictional pressure drop, and here L is the length of the pipe or tube or the duct, and D is the internal diameter if it is a circular pipe or tube, or as an equivalent hydraulic diameter if the cross section is non-circular, and rho, as you know, is the density and V is the velocity. So if you know the density, velocity, length, diameter, and this factor, then you can find out the frictional pressure drops. Now what is this factor F? Factor F is known as Darcy friction factor. It is a non-dimensional factor, and it depends upon Reynolds number and relative roughness of the internal surface. Now what is Reynolds number? I am sure that again you studied about Reynolds number in your course on fluid mechanics, but let me just give it for the sake of completion. Reynolds number is a dimensionless number that quantitatively relates the viscous and inertial forces, and whose value determines the transition from laminar to turbulent flow. So basically you have to keep it in mind that this is a dimensionless number, and it relates viscous and inertial forces, and its value determines whether the flow is laminar or turbulent. We will see little later what is mean by laminar or turbulent flow. And mathematically Reynolds number is expressed as Re is equal to rho Vd by mu, where rho is the density, V is the fluid velocity, and D is a length length scale parameter. If it is a tube or circular tube or pipe, D is the diameter. If it is a non-circular tube or pipe, D can be could be a hydraulic diameter. And if it is a flat external flow, that means the flow is taking place over a flat plate or something like that, then D can be the length. And mu here is the dynamic viscosity. So Reynolds number is nothing but rho Vd by mu. And for internal flows, it is observed that the flow will be laminar if Reynolds number is less than 2300, and the flow becomes turbulent if the Reynolds number increases beyond 2300. Now this is only a very rough criteria. Strictly speaking, you really don't have a sudden transition from laminar flow to turbulent flow. That means basically we will see, I will show you the boundary layer development. Generally you have at low Reynolds number you have laminar flow, and at a certain critical Reynolds number there will be transition. So that means the flow changes from laminar to a transition flow, and the transition flow continues to a certain extent, and beyond a certain Reynolds number the flow becomes turbulent. That means you have laminar flow, transition regime and turbulent regime. But for most of the practical purposes and most of the engineering calculations, we assume that when the Reynolds number, particularly for internal flows, if it is less than 2300, we take that the flow is laminar, and if it exceeds 2300, we assume that the flow is turbulent. But in advanced heat transfer and fluid mechanics problems, the transition region is also concerned. But as far as our refrigeration and air conditioning calculations are concerned, you may take the transition Reynolds number or critical Reynolds number as 2300 for internal flows. One more thing is that it is possible by carefully controlling the fluid flow conditions and all to extend the critical Reynolds number. That means you can have laminar flow even at Reynolds number as high as say 10,000 or 20,000 under carefully controlled conditions. So this critical Reynolds number and the number 2300 is a rough guideline. It is not a fixed number or anything. So we have I have mentioned that the Darcy friction factor is a function of Reynolds number and relative roughness of the internal surface. So let us look at a few cases. For fully developed laminar flow, the Darcy friction factor is given by 64 divided by the Reynolds number. That means for fully developed laminar flow, the friction factor is independent of the roughness of the surface, if it is only a function of the Reynolds number. And for fully developed turbulent flow, the correlation given here is known as Colebrook and White correlation. This is a Colebrook and White correlation, and it relates the friction factor with the roughness and the Reynolds number. This roughness has the same dimensions as the length scale, or that means the diameter. So this equation is a very popular equation, and it is known as Colebrook and White equation for the fully developed turbulent flow. One thing you can notice here is that to use this equation you have to use an iterative procedure, because f occurs both on the left hand side as well as on the right hand side. So you have to use a trial and error iterative method to find out f. Now ASHRAE suggests another correlation, very useful correlation and explicit correlation. First ASHRAE suggests, ASHRAE defines a parameter f1. f1 is given as 0.11 into Ks by D plus 0.68 divided by Reynolds number. So this factor is defined first, and if this factor is less than 0.018, then f1 is equal to friction factor f. And if the factor is less than 0.018, then friction factor is given by this equation. That means first you have to find out the factor f1 from the roughness and from the Reynolds number, and see whether the factor is greater than or equal to 0.018 or it is less than 0.018. If it is greater than or equal to 0.018, then f1 is nothing but f. If it is less than 0.018, you have to make a correction, and f is equal to 0.85 f1 plus 0.0028. So this is a very useful equation suggested by ASHRAE. Now I was talking about laminar flow and turbulent flow. Let me just explain laminar and turbulent flow and what do we mean by fully developed flow. Let us say that we have a flat plate over which fluid is flowing. So at this point you have what is known as a free stream, and this fluid comes in contact with a solid surface at this point. Let us say that at this point x is 0. So at this point the fluid comes in contact with the solid. Once the fluid comes in contact with the solid, what happens? Let us consider real fluids. That means let us say that the fluids have finite viscosity. As you know, viscosity is one of the transport properties of the fluid, and when a real fluid comes in contact with a, let us say, a stationary surface, then the velocity of the fluid adjacent to the stationary surface will be same as that of the stationary surface. That means the velocity next to the solid surface will be same as the solid surface temperature, solid surface velocity. And if the solid surface is stationary, solid surface velocity is 0. That means the fluid layer adjacent to the solid surface will be having a 0 velocity. That means velocity at this point will be 0. Okay, so suddenly the velocity changes from the free stream velocity to 0 velocity on the surface. Once the velocity is 0, you have to satisfy the continuity equation. That means a velocity profile will develop. The velocity profile will develop because of viscous effects. Since the velocity here is 0, the fluid layer on the surface will try to hold the fluid layer adjacent to it. That means it will try to decelerate the fluid that is adjacent to the layer, and that layer will try to decelerate the fluid that is flowing adjacent to it. So like that a velocity gradient develops, and that is what is shown here. So gradually velocity gradient develops, and at a certain point the velocity will be same as the free stream velocity. Again let us say that this is the free stream velocity. This is free stream on the plate, and this is the free stream velocity on the plate. Let us say that u infinity on the plate. Okay. So what basically has happened is, because of the presence of the solid surface, a velocity gradient has developed in this region, and the region in which the velocity varies from 0 to the free stream velocity is known as a boundary layer. That means this is known as a boundary layer. So because of the presence of a surface and because of the viscous effects, a boundary layer develops whenever the fluid comes in contact with a solid surface. Okay. Now initially this boundary layer will be laminar. So what do you mean by laminar? Laminar flow means the fluid particles will be flowing in layers or in lamina, and any mixing is only due to molecular motion. That means in laminar flow mixing between fluid layers is purely because of molecular motion, and there is no bulk mixing. Such a flow is called as laminar flow, and for laminar flow appears very smooth and it is steady, and a typical example of laminar flow is the flow of, let us say, a thick liquid like honey from a bottle. That means if you take a honey bottle and pour it, then the honey comes out in a laminar manner. Okay. And laminar flow is generally encountered when the Reynolds number is small. So at low Reynolds number you generally have laminar flow. So in this particular case, to start with, we have laminar region, and for this particular case we define Reynolds number in terms of the length scale. That means the local Reynolds number is defined as divided by mu. Okay. So here this length scale is x, or the distance from the leading edge. So as the distance from the leading edge increases, Reynolds number increases. That means Reynolds number increases in this direction. So to start with, we have a laminar region where the Reynolds number is small, and as I said, at certain critical Reynolds number the flow changes from laminar to transition. So you have a transition regime here. So transition regime continues to certain extent, and again at certain point flow transition takes place to turbulent region. So you have turbulent flow. So, to start with, you have laminar region, you have a transition region and a turbulent region. What happens in a turbulent region? In a turbulent region, you have molecular motion, and superimposed on that molecular motion is a bulk mixing of fluid particles because of eddies. That means in turbulent flow, eddies form, and these eddies lead to mixing on a bulk scale, that means on a macroscopic scale. So, you have mixing due to molecular motion as well as mixing due to eddies. So, this is the characteristic of a turbulent flow. And unlike laminar flow, turbulent flow is highly unsteady. And a typical example of a turbulent flow is, let us say that you have a water tap and you have opened the tap fully, then water comes out in a very haphazard and random irregular manner, and that is an example of turbulent flow. And you slowly close the water tap, then water becomes more and more regular, and at very low flow rates the flow becomes very smooth. That means you have a laminar region. So, this is how you can change the laminar region to turbulent region by changing the velocity in this case or Reynolds number. So, this is the in short the physics behind laminar and turbulent flows. And as I said, the value of Reynolds number decides whether the flow is laminar or turbulent. And for internal flows, I mentioned that if the Reynolds number is less than 2300, you have laminar flow, and if it is greater than 2300, you may consider that as turbulent flow. This is only a guideline. And for fluid flow over flat plate, that means the example that I have shown just now, the critical Reynolds number is totally different. So, for flow over a horizontal plate, the flow will be laminar as long as the Reynolds number is less than 5 into 10 to the power of 5. This is again a guideline. So, as long as Reynolds number is less than 5 into 10 to the power of 5, we assume the flow to be laminar, and if it exceeds 5 into 10 to the power of 5, we assume the flow to be turbulent. So, now let us look at the determination of minor losses. As I mentioned, minor losses are due to change in cross section and also due to change in the direction. Normally, when the cross section increases gradually or reduces gradually, there will not be any significant losses. But when the cross section increases steeply, then there will be boundary layer separation and there will be losses. So, these losses are known as minor losses. In addition to that, whenever there is a change in flow direction, basically an abrupt change, again if the change takes place gradually, then the losses are negligible. But if the change is abrupt, for example, you have a sudden elbow, then there is a sudden change in the direction, then you will have again pressure losses. So, the losses due to change in direction and change in cross section area are clubbed together and they are known as minor losses. So, generally the minor losses are given as delta Pm. This is the sum total of minor losses, and that is equal to K, a factor K into rho v square by 2. That means the minor losses are always proportional to the velocity pressure term. Okay. And this factor K has to be determined experimentally, and it will be different for different types of valves, joints, fittings, bends, etc. And generally the values of K for different fittings, valves, etc. are available in standard literature. So, what we have to do is, if you want to find out what is the minor loss, for example, you have a bend and you would like to find out what is the pressure loss due to bend, then first you have to find out what is the velocity pressure. That means you have to find out the velocity and you have to find out the term rho v square by 2 and multiply that into the factor K. So, this factor K has to be obtained from a published data for that particular bend or valve or fitting. So, this is generally the procedure for calculating minor losses. So, finally, the total head loss is nothing but the frictional loss plus minor loss. So, we have to find out these two. From that you have to find out the power required for a fan or pump, which is a typical problem in any fluid flow related problems in refrigeration and air conditioning. Now, let us conclude today's lecture. In today's lecture, we have reviewed the fundamentals of fluid flow relevant to refrigeration and air conditioning, and we have presented mathematical equations for conservation of mass and momentum, Conservation of mass is also known as equation for conservation of mass is also known as continuity equation. Both are same. And we have also presented and discussed Bernoulli equation in its original form, and also modified Bernoulli equation for viscous flows and when a fan or pump is used in the fluid flow conduit. Then we have presented methods for evaluating friction losses and minor losses with typical correlations for friction coefficients. Let me mention here that the correlations shown here for friction factor are typical correlation. That means there are a large number of correlations for different fluid flow situations, and these correlations are applicable. Generally they are empirical, so they are applicable for only that particular condition. That means every correlation has a range of application. So when you are applying empirical correlations, you must see what is its range of applicability and make sure that your problem falls into that range of applicability. Only then apply the correlation. And there are a large number of correlations available for friction factors for different types of flows. So depending upon the particular situation, we have to select a suitable correlation, then find the friction factor. Similarly, the minor losses, we have to find out the factor K depending upon the specific problem, and from these two we have to find out the total head loss. So these aspects have been discussed here, and we will be applying these to refrigeration and air conditioning in a later chapter. Okay, thank you.